Okay, so welcome to Math 150. This is going to be lecture 13, and this is going to be a mathematical tutorial. So what I want to do today is just talk to you a little bit about some of the things you can do using 21st century technology. And you should really get to the point where a lot of times your go-to for a problem is, let me write some quick code, let me gather some data, let me see what it's like. It is possible the data can mislead you, especially if you have somebody who is deliberately choosing what data to give you. But as a rule of thumb, it's very useful to be able to write some code, to explore, to get a sense, to get a feel of what's going on. I am old enough that I have lost track of how many computer languages I know how to use. Many of them you can find in the Smithsonian and other places where they preserve our history. Right? There are a lot of similarities from language to language to language. And there's a lot of great differences. Right? So a lot of times I use parentheses in this language and I use square brackets in this one. I start my counting at 0 here, but I start my counting with 1 over there. It can be a little bit confusing. So what I often do when I'm coding is I have two windows open. The main window, which I'm programming in, and the second window, let me make sure I remember how to do an if statement in this environment and just test some things there, run it, make sure it works, and then come back. I use Mathematica for many reasons. One, it's the first really serious calculation program I started to use, and there's a huge advantage to staying with what you know. If you really want to do a lot of computations that are extremely intense, there are other situations, there are other systems that might be better for what you want to do. MathWorks makes an absolutely wonderful project called MATLAB, and Simulink, which is wonderful for a lot of things if you need to do some high-speed computing. There's also languages like Sage, which a lot of mathematicians use, which is open source. So you can actually see how the code is written and how it actually computes things. A lot of times there's the danger of there is a black box and the computer returns an answer. Can you trust the answer? So can you actually do some tests to see, is the answer reasonable? And whenever possible, if you can have a feel for what the answer should be like before you do the calculation, that's great. Okay, so what I want to do today is just talk a little bit about the syntax of Mathematica and some of the stuff that we would want to do in this class. I have deliberately not prepared this lecture because this way I'm going to have to look things up. And you'll see, how do we look things up? It is very different now than when I first started using this product. How many of you have ever used a reference book or reference manual for a computer program? Not one hand. Okay, one hand kind of shook a little bit. Why doesn't anybody use reference manuals? What do you do instead? You look it up. How do you look it up? Yeah, how? On Google, you just search it on the internet, or oftentimes the programs now have huge help files. So you no longer have to have that. Now, to some extent, this is a little bit of a disadvantage. It's actually nice having a huge, thick book. Sometimes your table is a little, because you can actually then just read it and actually just see examples after examples. But there's so much online, you can find these there. All right, so let's start off by doing some simple things. If I want to add some things in Mathematica, 34 plus 17, I just put them in the, do shift enter and it adds them. Okay, what a shock. If I put a colon after it, it adds it, but it doesn't output the result. I can let x equal this, and now x is going to have that value. And so if I print x now, it will tell me what x is. If I print x minus 1, it will tell me that x minus 1 is 50, and it hasn't changed the value of x. Most functions are going to behave exactly as you would expect. I could let x be the cosine of pi. And so what would you expect that to be? -1. And so when I do shift enter, I get -1. So the key thing to notice here is that the way we do cosine is a capital COS. We then do the argument in square brackets, and then pi is just pi. Okay. What would happen if I actually wrote out cosine? It doesn't know what cosine is because it's defined cosine as that. Now, what I could do is I could define a function cosine, and then we do x underscore. So that's going to be my variable. And I will define that to be cosine of x. And now if I do cosine of pi, it will give me -1 because I've now defined a new function to be cosine. One of the things you might have noticed if you have really good eyes is as I start to type cosine, I hit a left bracket and it immediately gave me a right bracket. And the reason for this is Mathematica has a routine called "You are not an idiot" that's running in the background. And it's basically saying, my code had just put in a left bracket. They probably want to have a right bracket at some point anyway to finish it off. Why don't I be nice and just put that there for them? Okay, so it's a lot nicer in terms of than when I started because it does a lot of these things for you automatically. When you're old like me, you have to resist the temptation now to put in that extra bracket because it's already put in that bracket for you. What if I want to have a function of several variables? Well, I could do maybe f of x comma y, and then colon is equal as how you define something. So you should have hopefully seen this in some of your math classes. When I have a colon before an equal sign, it means what follows is the definition of the object on the left. If I just have an equal sign, it's just this is the value I have to do. So maybe I'm going to have it to be sine of x plus y. And now that's my function. You might remember this function from before, right? That was one of the functions we did a contour plot of. Well, if I want to plot this, I can now do plot 3D because it's going to be a three-dimensional plot, f of x comma y, and I'll do x goes from minus, let's do 4 pi to 4 pi. And then y is going to go from minus 4 pi to 4 pi. And so here's what the function looks like. And I can pick it up and I can move it around. I can control space and time to see what's the best way to look at it. And you can see, as we talked about, that it's going to be constant along lines, where y plus x is constant. This is not necessarily the easiest way to view it. Another way to view it is what's called a contour plot. And I'll just cut and paste from exactly above because I'll do the exact same thing. And so when I do my contour plot, let's see, I think it should be correct. Yes. And so here's my contour plot. And as I move my mouse over different parts of it, you can see over here, it's the value 0.8. Here's the value -0.8. And so you can see that here, over through here somewhere was the value of 0. And you can see that the function is constant along lines. It's just different ways of trying to display the same information. You might have seen this where you see some maps about the elevation in Williamstown or other parts of the country. Or you might have seen weather maps where you have lines of constant temperature. That's what we're doing over here with a level set. I'm showing you lines of constant value for the function. This is exactly the same information as what's above. Given that I have a two-dimensional screen, it's sometimes nice to display it on 2 dimensions. But again, we can simulate 3 dimensions very nicely with something like this, and I can move it around and see what's going on. So this gives you a little bit of a sense of the power. I can do a more basic function. Maybe I'll use g of x is going to be if x not equals 0. So the way you do a not is it's exclamation point equal sign. I think it's exponential -1 over x squared. And then if it is 0, it's going to be 0. All right, so this is an if statement. So this is a slightly non-standard definition of a function. So if x is not equal to 0, define it to be the exponential of -1 over x squared. And then if x happens to be 0, I'm going to define it to be 0. So let's plot this function. So I'm going to plot g of x. And let's have x go from -4 to 4. So this is the function we looked at earlier, where all of its Taylor coefficients at 0 are 0. When you look at this plot, it looks quite small near the origin, but it's hard to tell just how small. What we can do is we can zoom in. And so Mathematica has a wonderful thing called manipulate. And so what I'm going to do now is instead of plotting from -4 to 4, I'm going to plot from -c to c. And then I'm going to have c go from 4 to 0.0004. No, I'll do 0.004. That should be more than enough. And now what you can do is you can take a look. Here's my function. Here's my value of c. If I hit the plus sign, I can see the value down here. People able to see that it says the number 4? Okay. Now I can also make this into a movie so I don't have to do things. I'm going to have it go slowly. So I'm going to hit the slow button a few times. And then it's going to slowly decrease c, and you can see what's happening. All right, I've made it go too slow, so I'll speed it up a little bit. Speed up a little bit more. And you can start to see we're beginning to zoom in. Let's speed up a little bit more. I have to fill 50 minutes today, right? Right. We'll speed it up a little bit more. And now you can start to see as we're zooming in, it's getting really, really small. So again, what's nice about this is it allows you to explore lots of different things rather than, all right, I plotted it from -4 to 4. That turned out to be bad. Let me plot it from -2 to 2. Let me try -0.1 to This way I can just see many different things all at once. All right, if I give you a function, what might you want to do to the function? Yeah, take the derivative, or what else? Could find the limit at a certain point, but this is calculus. You're giving me half of the answer. Take the derivative is one thing, and integrate is the other. So let's see how to take the derivative. So take derivative of g of x. Let's see if this works. And it gives me 1 over e. All right, so let's see, what does derivative do? So I'm going to do question mark derivative represents the derivative. F is a function of 2 variables. Let me see. Oh, no, G was right. Okay, no, G was right. Okay. Derivative is the general form representing a function obtained by differentiating n1 times with respect to the first argument. So if I wanted to do this, I think I might have to put like a 1 over here and say I'm taking the derivative. But it somehow has G defined as 1 over E. So let's clear G. Well, let's take a new function. Let's take a simpler function. Let's take h of x to be x to the 4th plus exponential of x. We should be able to calculate the derivative of that without too much trouble. All right, so now when I'm trying to take the derivative, so maybe I don't have the x here. Okay, and so you can see it's giving me e to the argument plus 4 times the argument cubed. Does this look at all like a derivative as you're used to seeing? So using the word derivative is not the way that we want to take derivatives of functions. Mathematica understands that you're probably going to want to take a lot of derivatives. So they just have the big capital letter D stand for differentiator, take the derivative. So if I just do D of my function h of x as a function of x, should have put the x there. Yes. Unless somehow I'm having trouble with x. Okay, maybe the issue was I had used x earlier and I was having trouble defining it because I defined x to be something earlier. So if you're having issues like this, and again, this is why I did not want to prepare anything beforehand. It's good for you to see what happens when things go wrong. Did not kick and scream, did not start cursing. That's because I'm in public and this is being recorded. What you do is you think, what could I have done that's causing an issue? Clear question? Okay, so one thing is always just type the word clear all the variables, clear things like that. Sometimes just reboot the program, just close it and turn it back on. Sometimes what happens is you've got something in memory that you don't realize you have, and it's overriding something you think is free. Question? It is definitely case sensitive, absolutely case sensitive. All right, so now if I try derivative of h of x, it's giving me x. It's not giving me anything. But if I do h of x comma x, it's saying take the derivative of the function h of x with respect to x. And I'm getting e to the x plus 4x cubed. And so if I didn't have that, I got e to the x plus 4x. So it didn't know what to take the derivative to. So again, when you're not sure on what something is doing, just do question mark d, and it says dfx gives the partial derivative df dx. dfxn gives the multiple derivative. So if we want to take something n times, so if I want to take the derivative of this with respect to x 5 times, what do you think the derivative of h should be if I take 5 derivatives? If I take 5 derivatives of h, what should I get? I've got x to the 4th plus e to the x. What happens if I take 5 derivatives of x to the 4th? 0. What if I take 5 derivatives of e to the x? Yeah. So I should just get e to the x. And I get that. I could try taking the derivative of g of x. Let's not take 5 derivatives. Let's just take 1 derivative. So what's nice is Mathematica is incredibly intelligent. It says, hey, look, this was your strange function where you had a split definition. If x is not 0, it's defined as e to the negative 1 over x squared. If x equals 0, it's defined to be 0. And Mathematica computed and saw that when x is not equal to 0, oh, I can take the derivative, no problem. It's 2x e to the negative 1 over x squared divided by x to the 4th. And when x equals 0, it somehow knew how to use L'Hopital's rule and the limit definition and actually got the derivative of 0. Now, there are various things you could do. We might want to evaluate what that is. I can cut and paste that. And what I can do is I can define h1 of x. And I'll just paste that in here. And so now I could do the limit of h1 of x, x goes to 0. I think that's how you do the limit. Nope. So I did something wrong. So what should I do? Question mark, yeah, question mark limit. All right. And again, one of the things you can sometimes do is I can open a new notebook. For people in Zoom land, can you see the new window with limit?
Yeah.
Or is it showing the main thing?
Yes.
Okay. Okay, so it says limit fx goes to x star gives the limit as that. Okay, so I need to do an arrow. So let me try the limit. Let's take something where we understand what it is. Let's take x squared, x goes to 3. What should that be? I'm sorry? 8?
Oh, wait,
9. Okay, we got 9. Let's take the limit of x squared over 1 plus x squared as x goes to infinity. What should that go to? X squared over 1 plus x squared. Yes. Why 0? We have x squared over 1 plus x squared. So if x equals 100, you get 100 squared over 1 plus 100 squared. So it would be 10,000 over 10,001. If x is 1,000, you'd get 1,000 squared over 1 plus 1,000 squared. That's 1,000,000 over 1,000,001. So it should be going to 1. So let's check. So infinity, and so it's going to 1. So it now looks like I understand how to use the limit command. So let me toggle back. Can people see the main program now? Zoomland, can you see the main program? Zoomland, can somebody tell me if you can see the main sheet, please?
I can see the main sheet.
Okay, thank you. So we'll do, so the way you do an arrow is it's a minus sign, greater than sign, space, and now we'll take the limit as it goes to 0. And so it's able to identify that that limit actually is 0. You could, of course, do this the long way by using L'Hopital's rule, which will be a little bit painful, but you can do it. Now, let's have a little bit of fun. Let's take 2 derivatives now of g. All right, does everyone agree that this looks far more involved? So let's take this function. hate this computer. And I'm going to type simplify. Oops. I've just tried to set it up so I've got some blocks where it's going to put it in larger text. So simplify, and I'm going to put that thing over here and see if it can simplify it. And it is. So it is able to simplify that expression to something a lot easier to work with. I could have probably done that in the very beginning when I'm asking it to find the derivative of g twice. I could do simplify and just try putting that around it and see what it gives me. And so not only does it do it, but it actually prints it out in a very nice manner. It's equal to this nice expression if x is not 0, and 0 if x equals 0. And so if I give you any function and ask you to find the derivative, it's not a big deal anymore, right? So if I want to find the derivative of cosine of exponential of x squared over sine of x squared minus 11x plus 1,000 plus x to the 5th. And it's put in all the parentheses, so I think everything should be fine for me. And I'll take the derivative of that with respect to x. And it just calculates this. You should know how to do this. If I gave you this as a problem on your exam, would you be happy? No. But would you be able to do it? Yes. It's just being very patient and say, oh, good God, okay, I've got the cosine of the exponential. Okay. So as soon as I hear the word of, my first thought is it's a chain rule. So I'm going to have a sine of crap times a bunch of other things. And I can see the sine of crap over here. But again, the way Mathematica arranges things, it might put things in a different order than you would expect. I could ask Mathematica to integrate this. What do you think will happen if I ask it to integrate? Do you think it's going to give me a nice integral? No. Almost any function you put in is not going to have a nice integral. Well, we need to know how to integrate. So let's take some nice functions. Let's integrate the function x squared. So what should I get when I integrate x squared? So again, no. I'm sorry? X cubed over 3 or 1/3 x cubed, or maybe even a plus c. So for the exam, it's the material we've covered, but you also have to know how to do basic integrals, basic derivatives. Do you think this integrate command is correct, or do you think it's missing something? Yeah, with respect to what variable? Let's integrate with respect to x. And I get x cubed over 3. Can somebody give me another letter of the alphabet? Z, good choice. Let's skip over y. And if I integrate with respect to z, it gives me x squared z. X squared is a constant with respect to z. So when I integrate with respect to z, it's just viewing x squared as a constant. What if I want to integrate this from x goes from, say, 1 to 2? So I should have x squared becomes x cubed over 3. So I would have 4/3 minus 1/3, right? 4/3 minus 1/3 is 3/3, also known as 1. So this should be integrating the function x squared from 1 to 2. Let's see if it gives me 1. Does not. Did I make a mistake? Oh, I'm cubing it, not squaring it. Thank you. Okay, good. So it should have been 2 cubed over 3, which is 8/3 minus 1 cubed over 3. And it should be 7/3, not good. The other thing is, it's interesting to see which kinds of mistakes will be caught and not caught. I didn't want to do 0 to 1 because if you have squares or cubes of 0 and 1, if you have the wrong exponent, you're not going to notice. But as long as one of them is 2, you will notice something like this. So if I give you any integrals or derivatives to do, it's not going to be that bad. If I give you integrate x squared, say exponential of x, how should we integrate something like this? What method should we use? So what would our integration technique be for x squared e to the x? Why use substitution? If I gave you x squared e to the x times exponential of x squared, that would be u substitution. Let u equal x squared, and then du would be 2x dx. So this would be really good for u substitution. But I don't have that. I have x squared e to the x. So u substitution is a good thing to try, but it's not going to work here. What would be good for this? Integration by parts. How many times do you think we're going to have to integrate by parts? Twice. We have an x squared. If we integrate by parts once, the x squared is going to become an x. And so what I'll do is, I love cutting and pasting, so I'll do it two different ways. And so the first time I got e squared, the second time I got 2e squared minus e. And so Mathematica can handle stuff like that. If instead of integrating at x goes from 1 to 2, I could do the indefinite integral, and it's able to get that. So again, almost any of the stuff you need to do, these basic operations, Mathematica can do. What's the value you add? You tell Mathematica what to do. You choose what you want it to be exploring and computing. All right. What did we spend an entire chapter studying? All right, wait. Let me do one more thing here. We did Taylor series, right? So let's do the Taylor series of x. And says it's not a list with 3 elements. So what I have to do is I have to give you the variable, I have to give you the starting point, and I have to give you the number of terms I want. So I'm going to give the first 10 terms of the Taylor series of e to the x. Why do you think it's called series, not Taylor series? Think back to why we did d and not derivative. Why do you think we do d and not the word derivative? Yeah, it's convenient. You use it a lot. And so if you use something a lot, you like to have a shortcut name to it. Rather than writing cosine, we write COS. So we just write series for the Taylor series. And so it just gives us the Taylor series. Notice how it gives the denominators, 2, 6, 24, 120. It's not giving them as factorials, it's just computing them. If I wanted the exponential of x, you could start doing those derivatives if you wanted by hand, or just give it to Mathematica. If I gave you, say, y, x plus y, x goes from 0 to 10. Let's say y goes from 0 to 10. And now it's going to calculate out all the terms and just do a 2-dimensional Taylor series. Now, we haven't covered a 2-dimensional Taylor series. It's just nice to know that it's able to handle all of this stuff. Okay, so we did a whole chapter on vectors. So what's something we might want to do with vectors? Good, determine if something is orthogonal. So how do we tell if two things are orthogonal? So how do we take a dot product in Mathematica? Anybody know? What should I do? Let's look up dot. Dot ABC gives products of vectors, matrices, and tensors. Okay. And now when I click, okay, let me go to the other tab. Okay, people in Zoom land, can you see the new window?
Yes.
Zoom land, can you see the window where we have dot now written?
Yeah.
Okay, when I clicked on the arrow over here, it expands and gives me more information. I can look locally or I can go to the web. I'll just look locally. And it's going to open another window and it says dot or dot ABC gives products of vectors, matrices, and tensors. And so here's some examples. The scalar dot product is I can just do ABC dot XYZ and it's just going to give me the dot. I can actually have something that will calculate the angle directly. Rather than just coding the law of cosines, Mathematica is smart enough to realize, wait a minute, why not just have that as a predefined function? So a lot of the things you need are predefined. And if you're not sure if something exists, you search for it. You can type things up here in the search bar. You can go online and Google it. You can also scroll down and see a bunch of different things. And so, all right, so let me go back to the main code. And so I'm going to choose two vectors. I'm going to let v be the vector, let's do 1, 1, and semicolon to complete that, and u will be the vector 1, -1. So what should their dot product be? Should be 0, and I get 0. What should the length of each vector be? So the vectors are 1, 1, and 1, -1. What should their length be? Should be √2. So let me guess, does length give me the length of the vector? Length of v is 2. So do you think that it's off by a square root? How could you test to see if it's off by a square root? What could we do? I'm sorry? Okay, so let's let w equal 1 over square root of 2, 1 over square root of 2. What should the length of that vector be? What would the length of w be? 1. The length of w is also equal to 2. What do you think length is giving us? Let's take another vector where we understand. 3, 4. What should the length of that vector be? 5. We also get 2. What do you think length is giving us? The length of the list. Length is giving us the length of the list. So length is not the correct command here. It's telling us how many elements does W have. It might be norm. Let's try norm. So norm of 3, 4 is equal to 5. That's looking promising. Does anybody know another Pythagorean triple other than 3, 4, 5? 5, 12. So let's see if the norm of W is 13. More generally, I can do x comma y. Oh, good. It's giving me the square root of the absolute value of x squared plus the absolute value of y squared. So norm is giving me the length of the vector. Okay. So if I want to construct a unit vector, I could say unit v is equal to v divided by the norm of v. And then if I now do the norm of unit v, I get 1. So whenever possible, try to have good names for things. If I want to do the cross product, I really want to have things with 3 components. So I could do maybe u equals 1, 1, 1, v equals 1, -1, 2. And then let's try looking up cross product. Missing, so unknown. So let me try looking up cross. Cross gives the vector cross product of A and B. Okay, so pretty natural name. Let's do u comma v. And we get 3, -1, -2. Unfortunately, I can't really just look at that and see, is this correct? So we could start putting in various vectors to see if we know. But what's one test we could do to see if this is correct? If this truly is the cross product of uv, it should have a nice property. What would be that nice property? It should be orthogonal or perpendicular to u and v. So let's dot it with u, we get 0. Let's dot it with v, we get 0. So that shows you that we at least got a vector that has the right direction. So this is not a proof, but it's pretty indicative. The other thing to note is as I started typing cross, it starts suggesting things that you might want. And so, I'm not sure, is it cross product or whatnot? Okay, I don't see cross product listed, but I see cross matrix. I see cross as the first natural choice, but then there's also cross matrix, cross entropy, loss layer, crossing detect, crossing count. I can start to see more things, but it tries to suggest what you might want to do. So it's extremely helpful. We might want to do some determinants. So here's one of my favorite matrices. I'm going to do M for matrix. The first row is going to be 1, 2, 3. The next row is 4, 5, 6. And the next row is 7, 8, 9. And I'll also do a 2 by 2 matrix. 1, 2, 3, 4. So what you need to know when we're doing matrices is you do it row by row by row. You start off with a left parenthesis, right parenthesis to basically say, I have a list. And the first element of the list is the first row. The second element of the list is the second row. Does that look like a matrix to you when you see this? So I am old. Because I'm old, I would just type matrix form M. Oh, it actually worked. Okay. Sometimes what you have to do is it calculates the matrix form, but it doesn't necessarily print it. Sometimes you have to put in the command print matrix form and just print it out. But it doesn't seem like you needed that. And so I can do print matrix form of big M. And so it's printing those matrices. And that's a lot easier to view. You want to make things as nice as possible. I am not putting in comments because this is your pretty straightforward stuff right now. What might you want to do to these matrices? What might you want to find? The determinant. So what do you think is the command for determinant? What would you guess? DET for determinant. And so I'll do determinant of M, and I'll do determinant of big M. And so the determinant of the first one is -2. The determinant of the second one is 0. Let's do M4. The 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'll do matrix form of M4, and then I will do determinant of M4. And we see M4 has determinant 0. M3 had determinant 0. M1 is just going to have determinant 1. It's just the 1 by 1 matrix 1. M2 has determinant -2. The next two numbers are 0 and 0. What do you think the determinant of M5 might be? I'm sorry? 0. And M6? 0. So let's try to figure this out. Who wants to see me writing longer and longer and longer lists by hand? So this is a good chance to start talking to you about how can we do some coding. All right, so what I'm going to do is big matrix, and it's going to have n as a variable. So module just means I'm making some program. It's a function. This curly braces here means I have no local variables. And so what I'm going to do is I'm going to define my list to be empty, and that's going to be my matrix. And I'm going to define, let's see, for I equals 1, I less than equal to n, I plus plus, this is going to be my for loop. And it put those braces, and so I'm going to start putting in some comments. End of the I loop. And over here, end of the module. This list will be my matrix. Well, no, we're working on this together. It will be our matrix. All right. And so now what I'm going to do is I'm going to build it up row by row. So cur row is empty. So that's going to stand for the current row initialized to 0. Now, I is going to go from 1 to n. Okay. And so what I'm going to do now is cur row is equal to, I'm going to append to the current row, and I need to know the number. So the first number I add is 1, then 2, then 3. So if I'm in row I, I'm adding, well, let's do it this way. I'm going to have I go from 0 to n minus 1. So I'm going to add I times n plus j. And so now what I'm going to do is that this is going to be a for j equals 1, j less than equal to n, j plus plus. And then this is what I'm going to be doing. End of the j statement. So what I'm doing is I'm adding an element by element by element. So initially I is equal to 0. So I'm adding 1, 2, 3, all the way up to n. Then the next time I come through this, I is now equal to 1. So I'm going to add n plus 1, n plus 2, all the way up to n plus n. And the last time I get through, and so now after I finish the j loop, now what I want to do is I want to put this in as my next row. So now list equals append to list the current row. And now let's print matrix form of list. So that'll print it out, and then print determinant of list. So hopefully this will work. So we called this big matrix. Let's do 4. And it worked. So now what I could do is I could do for n equals 1, n less than equal to 20, n plus plus, and then I'm going to run big matrix at n. And you can see, it's printing out all the matrices, it's printing out things like this. It's getting a little bit hard to read, so maybe I could do a little bit better job with how I write things out. So I'm going to print over here, n equals, and then I'm going to print n. And matrix is, and then I'm going to print the matrix. And determinant is, so hopefully that's done it correctly. And now it's a little bit easier to read. And so this should give us some really strong ideas about what's going on. All of these seem to be 0. Let's choose just a very large value of n. Can somebody give me a large value of n that might be good for this class? What's a good big number related to this class? 150, right? Do you really want to see me enter 150? No. Let's just do big matrix of 150. And it printed it out. Here's the matrix. And you can see the first row goes 1, 2, 3, then 151, 3. Oh, hey, it's working. And if I go all the way down, n equals 150, and the matrix is, and now to find the determinant, unfortunately, it's going to be all the way at the end. Also, I might have to scroll up now, and the determinant is 0. All right. This should be enough to convince you that if I take the numbers 1 through n squared, as long as n is at least 3, the determinant is 0. So for extra credit, you actually know enough to prove this if you remember geometrically what the determinant is. It's the volume of the parallel pipette. So what does it mean for it to be 0? It means somehow the directions are not independent. So if you can figure out how this implies, if you were doing something just once in your life, is it worth making it efficient? Probably not. If you only have to run it once, don't spend too much time on it. But if you're going to be doing it again and again and again, it's worthwhile thinking, how can I do this efficiently? And so for this matrix, if I want to look at a lot of matrices, I don't want to be inputting all of these by hand. I want to just construct a little procedure. And again, one of the most valuable skills you can have when you leave Williams is the ability to write simple code. I don't care what language you use. I like Mathematica. It has a lot of really nice predefined functions. It has a lot of wonderful graphical interfaces, but you can do it in almost any environment you want. And what I wanted you to see today is a lot of the stuff we're doing, finding determinants, finding cross products, finding dot products, integrating, differentiating, plotting. We can do all of that easily. You should be able to do these problems by hand. This doesn't mean you want to be able to do them by hand, right? Is there anybody who multiplies huge numbers without using a calculator? No, the calculator is a tool. This is a tool. You need to learn how to use tools like this. At some point during the semester, I will bring down the small table of integrals that I was told to have on me at all times and the big monster that I was told to keep in my room for serious problems. And again, I'm old enough that when I went to school, this is what you did. And you paid big money to have a huge table of integrals. Now, it had more than just table of integrals. It had lots of wonderful functions and whatnot, but you had to learn how to use it. How many of you had to learn how to use tables of integrals? So you would have to learn, how do I convert my problem so that it looks like what's in the table? So earlier we had a suggestion of, let's try U substitution. Wouldn't it be nice if the computer just said, let me try a bunch of natural U substitutions and see if I can convert this to something I already know? And that's what it does now. But in the old days, you had to figure out, let me see if I can convert this to something that might be in one of the tables. And you might have learned this something called trig substitution. And if I have 1 plus x squared, I use this. If I have 1 minus x squared, I use that. And I have all these different rules to try to remember which one do I use and when. So again, there's a lot more you can do with this. I have linked at the very top of the sheet, and I will be sending this to everybody, just some lectures and some tutorials online that I've done in some notebooks on just how to solve problems with this. In a complete shock, I have decided to make my Math of Sports class today also be a coding day. And so I'll be doing some more advanced coding with them. If anybody wants to stay at 10 o'clock, you're welcome to. I will post those videos online and give you the links to those and just show you how to solve things like the dot theta problem and the double sixes problem. All right, so this is a good place to stop.